Alright, so in drill 3.7 and 3.8, you just have to evaluate the divergence. That's it, so not a big deal for you. Remember that while evaluating divergence, you should take care of the coordinate system you are working in. So for a spherical coordinate system, the formula for divergence is different. For cylindrical coordinate is different. For rectangular coordinate it's different. And the latest edition of your book, 8th edition, the formula for divergence in all the three coordinate systems are given on page number 62, equation number 15 for rectangular, 16 for cylindrical, 17 for spherical coordinate system. By the way, these formulae are also given at the back cover of your book as well. And never mind, you don't have to remember these formula, because these formula will be given to you in exams. So let's discuss the last drill problem of this chapter, which is 3.9. Electric flux density is given to us in coulombs per meter square, and we are given a region which is identified by these 5 surfaces, and we are asked to find the both sides of divergence theorem. So divergence theorem, in case you don't know, we have also covered that in lectures, but in case you missed it, so this is divergence theorem. So we have to evaluate both sides of divergence theorem. And yeah, so first of all, identify this region. If you are able to identify this region correctly, then that should not be evaluation should not be a problem. Evaluation of both sides should not be a problem for you. Why? Because for left hand side especially, you have to consider the surfaces. So remember, surfaces are not scalar quantities, they are vector quantities. So if you are able to identify the surfaces correctly, you will be able to identify the directions of those surfaces correctly. If you take any direction wrong, whole problem will become meaningless, or will give you wrong results. While evaluating the right hand side should not be a problem for you. Why? Because we have to deal with the volume, and volume is a scalar quantity. So this region is, rho is equals to 2 is an infinite cylinder which has got the central axis as the z-axis, length infinite from minus infinity to plus infinity in terms of z, and radius is 2. So imagine that there is a cylinder like this, and we have to evaluate divergence theorem on this surface. So definitely, if we want to find divergence theorem, so remember that these 5 surfaces must define some closed volume, otherwise divergence theorem cannot be applied. All right, and recall this, that the relationship between the left hand side and right hand side terms is that on the left hand side, the surface, on the right hand side, the volume over which we have to evaluate the divergence theorem, or this term, or this integral. This volume is actually the volume which is occupied by this closed surface. So there is a relationship between this surface and this volume. So remember, this region must define a closed surface, otherwise we cannot find divergence theorem, because divergence theorem is applied over closed surfaces. So this is rho is equals to 2, infinite cylinder, but it is open from the top and the bottom. Remember that it's hollow cylinder. So from the bottom, this cylinder is covered by z equals to 0. Okay, fine, xy plane, and on the top it is covered by z equals to 5. But it also says that no, we are not interested in a whole of this cylinder, rather we are interested in that portion of the cylinder which has the values of phi from 0 to pi. So phi is always, phi equals to 0 is a radial plane which starts from z-axis and go the other side, and the other side, which side, is defined by this angle. So actually xz plane, if I take the positive side of xz plane, meaning this, So this is actually phi equals to 0, because if you move on this plane, phi is equals to 0. And if I take negative should not be messy. If I take the negative x and z plane, meaning this one, so this is phi is equals to pi. So this one is phi is equals to 0. So we have got two planes, radial planes. Okay, so and definitely it's cylinder. So I should draw it like this. So actually this, no, it should be like this. So this half cylinder is the one over which we will have to evaluate the divergence theorem. Okay, so the radius of this cylindrical surface is 2. At the top is z equals to, this top is z equals to 5, and this bottom is definitely z is equals to 0, and this shaded plane is phi equals to 0 plane, and this shaded plane is phi is equals to pi plane. So this is the region over which we have to calculate. So left hand side, okay, once we have defined this, left hand side of this divergence theorem is this. So now definitely ds for this surface is different, for this is different, for this is different, so we will have to divide it in 5 surfaces. D dot ds for rho plus d dot ds for phi equals 0 plus no, I should not use the closed loop now, because individually all the surfaces are open, combined they are forming a closed surface. D dot ds for phi equals to what? Phi equals to pi plus d dot ds for z equals 0 plus d dot ds for z equals to 5. Now before starting this, let's see the directions of this electric flux density. Electric flux density has got a rho component which lies on the horizontal plane, phi component which lies on the horizontal plane. Okay, so this d will always be on horizontal plane. The direction of field will always be on horizontal plane. So if you will try to calculate these two integrals, this is for z equals 0 plane, so it means that this is on horizontal plane and this is something perpendicular to horizontal plane. This is for horizontal plane, this is something perpendicular to horizontal plane. So by inspection I can say that we don't have to evaluate this. By inspection we can say that this these two integrals will be 0. So let's give this equation a number, equation number 1. So let's try to find this d dot ds for rho. So for rho, we know that for rho, this cylindrical surface, so for a cylindrical surface we know that the formula for the cylindrical surface over which rho is constant is given by rho d phi dz a rho. Okay, so this is the direction of the patch. So instead of writing whole of this d, I should take the first component only. Why? Because the ds got has the ds has got only one component, so I should not write, waste time in writing the second one. So I should consider, you should write a one liner here, that since the surface area has got only rho component, so writing the rho component only. Okay, so integral, double integral 6 rho sine half phi arrow dotted with rho d phi dz arrow, limits for phi and z. Dot product, take the dot product, arrow dot arrow will be 1, only magnitudes will remain, and constant should be taken out. So 6 should be taken out, rho square should be taken out, and in integral we should have sine half phi d phi. Okay, I hope I'm not missing any. Yeah, and dz. Z from where to where? From 0 to 5, and rho from 5 from 0 to pi, and now the value of rho is how much? The value of rho is 2, so 2 squared. Integrate this one, you should have minus cos 0.5 phi divided by 0.5, meaning multiply by 2. So instead, I should write 2 here, 2, and limits from 0 to pi, and integrate this, you will get 5 minus 0, so I'm just writing 5 here. So और 240 6 2 2 2 5 240 cos of, and I should write minus here, so cos of pi by 2 is 0, minus cos of 0 is 1, so plus 240 coulombs. बहुत ज़्यादा फ्लक्स यहाँ से निकल रहा है, 240 coulombs का flux. Anyway, so now for the second, where phi is 0, d dot ds, what I can do is, we are interested in now this patch on phi equals to 0. But now this patch, the formula for this patch, ds phi equals 0 should be, this length is d rho, this length is dz, so d rho dz. Okay, how about the direction? Direction should be a phi, but a phi is what? A phi is in this direction. If you see it from top, a phi is in this direction, which is pointing into the volume, contrary to our traditions, contrary to our convention. So we should take the direction which is perpendicular to this patch and pointing out of the volume, so minus. Okay, so as a teaser, for the second, for the third volume, for the third integral, meaning this one, the ds for phi equals pi, this length is again d rho, this length is dz, so d rho dz. Okay, and because for this surface phi is constant, so a phi. Okay, so for this surface, a phi is already pointing in this direction. If you see it from the top, what you'll see, this is, let's say, x-axis, this is y-axis, So this is the semi cylinder. This is phi equals to 0 and this is phi equals to pi. So the directions should be perpendicular to phi equals to 0. If I take a phi, this is a phi, but this is pointing into the volume. No, we are not interested in that. We are interested in a direction which is pointing out of the volume. So I should say take minus a phi. And for this phi is equals to pi surface, the direction of a phi is already this, because if you move in this direction, the angle of the plane will increase. So this direction is a phi. How weird, right? This direction for phi is equals to 0. This direction is minus a phi. For phi is equals to pi, this direction is a phi. That's the things which you should be, really comfortable with now. Okay, so let's talk about this one. So the direction, direction or the component of ds which is available as phi. So we should not write the whole of the d. Rather, you should write one line statement and just write the second component, which is 1.5 rho cos of half phi a phi dotted with this, which is minus, instead of writing minus here, I am taking minus out, d rho dz a phi. So now take the constants out, minus 1.5, and now variables are phi, rho and z. So phi's are constants. So okay, so integral, I hope I haven't left anything. Integral rho d rho from 0 to 2, from this to this, 0 to 2, multiply by integral dz from 0 to 5. So minus 1.5 cos, for this whole radial plane 5 is 0, so cos 0 is 1, so I should write 1 here. So integrate this, rho square upon 2, limits from 0 to 2 and 5. Okay, so okay, so minus 1.5 upon 2, let's see, minus 1.5 upon 2 multiply by 5, 2 2s are 4. Okay, so cancel it. What will be left with? 15. Okay, 10, 15, minus 15 coulombs. Now for the third integral, we'll do the same thing. We'll start from here. Instead of phi equals 0, we'll write phi is equals to pi. Okay, so phi equals to pi. Rest of the thing will be the same here. Okay, only the thing is that instead of minus there should be plus, because there is no minus here, but it does not matter. Why? Because when you will proceed to the next stage, you will have a plus sign here and rest of the things will be the same. As soon as you will put the value of phi equals to pi, cos pi by 2 will be 0, so this term will turn out to be 0 later on. So from equation number 1, the left hand side, which is nothing but d dot ds closed loop integral, will be equals to 240 minus 15, 250 coulombs, left hand side. I hope you are able to see it. Yes, alhamdulillah, you're able to see it. So now the right hand side is easier to evaluate. Remember this value 225, so I'm rubbing it. 225, 225, 225 coulombs. 225, 225, 225. Okay, ji. So for right hand side, integral. This is triple integral, volume integral, del dot d dv. Okay. So let's calculate del dot d. Page number 62. Page number 62 of your book. Formula for divergence has got this form: 1 upon rho dava over dava rho dava rho 1 upon, I hope I am writing it correctly, dava d phi over dava phi plus dava dz or dava z. This is the formula for divergence in the cylindrical coordinate system. So since d has not any z component, so we are not interested in the z component. Wow, great. So 1 upon rho, take the rho component and multiply it by rho. So dava over dava rho 6 rho into rho, meaning 6 rho square. So take 6 here, rho square inside, and sine of half phi inside. Okay, and 1 upon rho times dava d phi, this phi component, 1 upon 1.5, so I can take 1.5 out, and I should write cos half phi alone, and I should take the rho outside because this is partial derivative. Okay, nothing I am not missing. I hope I am not missing anything. So this is d dot d, divergence. So divergence, let's see if I'm missing something, so I'll get the wrong answer. We'll trace it then. Okay, so 6 upon rho, and this should be constant because derivation is with respect to rho. So sine half phi. So if you differentiate, you'll get 2 rho se rho cancel. Anyway, let's proceed. Plus 1.5, and this should give us what? Cos का derivative होता है sine minus sine. So minus should come here, minus sine half, और इसको half से multiply करते हैं, multiply करेंगे ना. So 12 sine half phi minus 3.3 by 4, 0.75 sine of half phi. कितना हुआ? 11.25 sine of half phi. This is divergence of d, and I sincerely hope that I'm not missing anything. So I think we don't need this diagram anymore. So the right hand side is triple integral divergence, which is 11.5 zarab sine half phi, and d rho differential volume is very easy in Cartesian coordinate system. So जनाबे वाली 11 integral and sorry, what the nonsense I'm doing. We are working in cylindrical coordinate system, so rho d phi dz. So rho d rho here sine half phi d phi here dz 0 से 5 0 से 2 0 से पाई जनाब 11.25 रो स्क्वायर बड़ा 2 0 से 2 मनफी कॉस ये कहाँ से कहाँ तक 0 से पाई ज़रब 5, ये क्या बनेगा, जो भी बनेगा 11.25 बटा 2 ज़रब 4, ये माइनस यहाँ पे cos of pi by 2 is 0 minus cos of 0 1 ज़रब 5, क्या बना, ये माइनस उसको मनफी ज़रब मनफी मस्बत 11.25 ज़रब 2 ज़रब 5, क्या बना, कुछ और ही बन रहा है। क्या गड़बड़ हो गया, टू टू द 4 0 से 2 तक था ये, बताइए। वैल्यू जो है वो एग्जैक्टली आधी आ रही है, कहने को गड़बड़ भी है। वी हैव डन some problem somewhere, some mathematical glitches somewhere. Let me figure it out. हाँ जी, पकड़ा गया। ये what we have done, we should multiply it by 2 while taking the integration. So it should be 2 multiplied by this. So there should be 2 here. So there should be 11.25, 2, then 2, then 5. So if you multiply it, you will get the answer 225 coulomb. Right hand side is equal to left hand side. Proven.